Hello everyone. Let's do another Leetcode question today. I think it'll be kind of fun to try a medium question. I haven't done it in quite a while, so I'm going to be quite rusty, so please bear with me. If you're interested in following along, I'll have the link below in the description, as well as time codes for different sections. So let's choose one at random and see what we get. Okay, so we're getting number 2265. Count nodes equal to average of subtree. Given the root of a binary tree, return the number of nodes where the value of the node is equal to the average of the values in its subtree. Note, the average of n elements is a sum divided by n, rounded down to the nearest integer, so integer average. A subtree of root is a tree consisting of root and all its descendants. So given the root, find the number of nodes where the value of that node is equal to the average of the values in its subtree. So if it was, let's say, just one element, then it would be true, the root by itself, because the average would be just it. Each node has, it looks like they provided a little bit of code for us, so I'll copy this over at least. And let's clean this up. And so here in this example, 8 is not because 0 and 1 average is 0. 5 is not because the average of 6 and, or is it because the average of 6 is just by itself? It's just the children, average of its children, not including itself, which makes sense. So 5 is not, but 5 and 8 is not either. Oh wait, is it? No. Here the output is 5. The number of nodes, there's 5 nodes that have an equal, I guess the base, 1, 2, 3 at the bottom. The average of its subtree is 4. Oh, because it sums up all the values inside the subtree. It doesn't care about just the children, it's all the children. Okay. So 8, 9 plus 11, 20 divided by 1, 2, 3, 4, 5. 20 divided by 5 is 4. Or is 24 divided by 6, 3, 4, 5. It includes itself. All right, so it does include itself, consists of the root and all of its descendants. Sorry, I should have been more clear on that. Okay, so what we're trying to do is find a way to calculate the average of all of the nodes, as well as, so we can kind of start talking about this with like the Brutus approach, which is given a root, calculate count of all children and all nodes under it, and sum of all nodes under it. And then you just return if the average, the sum count, sum divided by the count is equal to the value of the node, root.value, in this case val. So that's one way you could do this. For every call, you'd want to calculate the nodes all under it, and you can do that by just recursively calling for each subnode. So for example, you get the root. Let's start writing a kind of a rough script, because I think this will apply to all of them. So let's say average of subtree. And the input will be our, I guess, root, and it'll be a type node, tree node. And our output will be a Boolean for true or false. So then we'll want to return the int of the sum divided by, well, we'll call this total, divided by count is equal to root.val. and total and count equals, and we'll create a new subtree node. Descend, let's call it descend the root, and our initial values will be 0 and 0. Actually, I guess we'll include the current root dot val and 1. Is that the right way to do this? I guess we'll find out. So let's do it the other way around. We have our descend, we have our node, and let's just call this node. And it's, what we'd like it to return is 2 ints in a pair. Returns total number of nodes, sorry, sum of values and number of nodes. So if the node doesn't have children, is leaf, return just the current node's value, and the number of children is just itself 1. So how do you check if it's a leaf? We check if not self.left and not self.right. Otherwise, we will get the descend to left. And actually what we can even do is if not node, return 0 and 0. And then I don't think we need to do this anymore, because it's not there. So take the descend self.left and plus left val, left total, left count, and right total and right count. And I don't want to get too far into this because we might want to try a different approach than the brute force approach. But I do want to actually have a general process here, just so we have something to work with in case we run out of time. So total equals left.total plus right.total plus this val, node.val, and count equals left.total plus right.total plus 1 for itself. And we just return the total and count. So let's make sure this makes sense. If we descend and there's no children to the left, it returns a 0 and a 0, and to the right a 0 and 0 if it's not there. Otherwise, it'll descend down them, and for them it'll do the same thing, so on and so forth, adding itself every time as needed. So if it was like a leaf node, it would get zeros for both of them, but it would include its own value plus 1. Okay. So descend gives you what we're looking for here. And this should be one approach to solve this problem. This is a brute force approach, and so what that means is, well, it's going to iterate through all of the nodes, but it's not going to go more than once through all nodes, i.e. O of n for n nodes. Time complexity, so it's not that bad actually. And then for space, it'll also be O of n in the worst case as you spread out to all your children. Okay, so we can have null, yeah, that's fine in root 1. Some checks to be had here is how big the tree would be. It looks like we're given the range of nodes, and the values are all going to be legal. These are all questions to ask, as you've seen in my other videos, is whether we need to deal with any edge cases, such as invalid inputs or invalid values within, whether the sum of the values will, like a common one is, will the sum of values overflow an int? And in Leetcode, the answer is no in this case because they're all 1,000 nodes, 1,000 max value and 1,000 nodes. So that's what 1,000,000 is the max int, and an actual max int 2 to the 32 minus 1 is like 4 billion or something along those lines. Might be one more than that. So 4 trillion. I'm not entirely sure. Either way, don't have to worry about it now, but it's a good question to ask your interviewer in case that might be relevant. In terms of space is O(n), in terms of iteration is O(n). We are doing this recursively, so brute and recursive. So one could do this iteratively instead of having this descending node call itself. The advantage of doing recursive is it's a lot cleaner most of the time, so it's easy to understand. But then you're relying on the computer's stack memory to deal with this. So the stack memory might have a limit. Like if this depth of the tree was more than the stack memory of the machine running it, then you would run into a Stack Overflow error. In that case, iterative would be a lot better, which may or may not come into play in this one. So that's a good question, because we could have a tree that's just one child each, and it's going all the way down to 1,000. But I think stack can hold that. I suppose we'll find out. Shall we have a look and see if this works? Let's find out. And we're going to have to, let's create this function too. We'll have to modify this to deal with solution. So descend. Okay, and you're all able to see this, I hope. Yeah, good. Just in case. And we'll have to do self.descend here. Same here as well. So hopefully this is O of n and O of n times space for n nodes. Let's have a look and see if it works. I was tempted to spend a little more time trying to run this, and oh, self.left and self.right. Well, there's your answer. Make sure to double check your typos. These need to be the nodes, not the self. You may have seen that while I was typing it up and probably were yelling, so apologies. All right, is there any other ones I'm trying to see now? Now that I've proven that it's important to double check. We've got a root, we got a root val. I chose node. I'm happy I used a different word here just because it's a little easier to see the difference between those two. The total divided by the count, integer to round down. Okay, let's find out. Oh, we're supposed to return the count of all the nodes, not just the value itself. So good thing we finally saw that right here. I think the interviewer would have pointed it out. So the goal is not just to return this, it's actually to return the count. So what I'd like to do is actually get I'd like to create another function that works hand in hand with this. And well, no, let's change this to, I'd like to descend and valid is what I'd like to get back. I guess we don't really need the total here. What we want is valid, and that's going to be the value that comes out. And here I'm calling valid is the node count of nodes with average equal subtree, including itself. So total and count ends up being unused in these cases, and that's okay. But here we're going to return valid as well. So 0 for that because there's none for that one. So what we do now is valid is equal to the int of total divided by count divided by this current node's value. And then we return valid equals, we have left valid and right valid. And we do the same thing here. And it just basically percolates up all the valid nodes that were included. I think you can add a Boolean directly as a 1, but I want to make it extra clear. So like, let's just say 1 if this is true, else 0. And instead of is valid, node valid. So we add whether the subtrees to the left and right are valid, the valid node counts, and then we also add ourselves if we are valid as well. And then we return that, and that percolates eventually to the top, and that's the one we end up returning. So let's modify all of this. I'd like to make sure everyone can see this, so let's pull this over. Left, right, self-valid, return empty otherwise. This is just an inline if statement. It returns 1 if that is true. Otherwise, it returns 0. Yeah. And then we return the sum of all those 3 together. And it uses those values as needed. Okay. So one thing we could do now is we could either run this with an example, and perhaps that's the right approach here. So let's just do the simplest example here for just one root node. So we call descend on root node, root val is 1, no children. So what does it do? It'll call descend on the root. It'll check if not node, it is a node. So we continue. We descend left, it's going to call on if not node, so it'll get zeros for everything. Same for the right. Good thing we did that check. Good thing we did that check. And then it'll sum up the left, right, plus its current value. It'll count the left, right, and the count of the current value. And it'll say if the current node is valid if the int of the total, which in this case is just the current value divided by count, which is 1, so it'll just become the value. And this will become true, so the node valid becomes 1. So valid becomes 0 plus 1, so it returns 1, which is the correct answer for this case. So I think this should work. So I'm going to go ahead and say let's have a go and do a quick test on the test cases, see how it looks. I'm hoping this is, oof, never mind. So it's right on that case, but wrong on this one. And we got an output of 3 instead of 5. So what's going on here? Why are we getting 3 instead of 5? We're descending to the left, we're descending to the right, we're including the current value. Are we not counting the number of valid cases correctly? We're not counting when if we're a leaf node, I guess we should try to do a check. Let's run through the example here and make sure we're doing the right thing. So example 1. So called on descend on node 4. And what it'll do is it'll get the left and right counts. So the left counts will be descending on the node left, which is the 8, and then it'll do the same thing. It'll descend for 0. And this should pass just fine because we're checking if the node itself is empty or not whether the value of the node is 0. So I don't think we have to worry about that. I'm just making sure none is the default if it doesn't exist. Yeah, left, right, none. Okay. I guess we do a little print right here and see how we're doing, just to print node of val node. Just because I'd like to see what's going on at this point. You can't really do this in an interview, so we're already at the wrong step. But here, I just wanted to see, like, so we descended all the way to 0, which is correct. Zeros on either side. Maybe we should do a check to see what it actually puts out. Total count valid. Let's try that. Yeah, so that's good. This one was valid once. 1 is also valid. 8 has only 2 valids because it itself is not valid. Uh, 6 is valid by itself. 5 is not valid by itself, so it just includes 1. And then 4 gets the sum of 1 plus 2, 3, and it should have been, oh, that's why it gets 3, but it didn't return itself. Because we had 24 divided by 21, and it should have been 24 divided by 6. Oh, the counts are increasing too quickly, it looks like. Eight's count should have been left and right plus 1. So 1, 1, 2. I wonder why. Interesting. Total count invalid. Total count invalid. Oh, it was a typo. Left count, right count. Apologies, you guys may have been kicking me for this one. You saw it coming from a mile away. Took me a while to realize that that was the case, so let's fix that over here. And I think that should get us close / hopefully to the right answer. So let's have a look and see how we're doing here. Yeah, there we go. The 2 cases are correct. Let's submit and see how we do. And it was accepted. Great to see. All right, I'm happy with that. I'm a little disappointed that I didn't catch this little typo error. Like, the good news is if you're doing an interview with the interviewer, they'll kind of ask you like, oh, are you noticing any typos or errors that you have? And running through an example, kind of like I did, helps you find these kind of off by 1 errors. I get a bit of tunnel vision when I'm writing code sometimes, and it's totally normal to miss things. As long as you're able to kind of find it, especially when hinted to, not a big deal. This doesn't signify the worst about a interview candidate. Getting to this logic is pretty good. So I'm happy with that. Happy to see that it runs. Again, don't worry too much about speeds unless it's kind of hard to do this any more inefficiently than this. It's possible to get more efficient if you can bring this into a iterative loop, which we may or may not explore. But we did pretty good. I'd say for a medium question, about 25 minutes, not bad. This was a relatively straightforward one. I could see something like this being given in an interview question. All right, so let's just quickly talk our way through some alternatives. So approach 2 is iterative. So here, instead of recursive calls, use a stack or queue to keep track of the children nodes. Alternatively, you can memoize. I guess that doesn't really make sense. Alternatively, what you could try to do is find all the leaf nodes first, you know what they are, and then percolate it backwards. So you could build a graph. You can either use a stack or queue. You can also build a table graph. It could even be a dict for all the connections between each of the nodes, and store your information there. I'm not going to go through and implement these just yet. I'll leave that as an exercise for the viewer. If you do go ahead and do that yourself, please let me know. I'd love to see kind of the approaches you follow. Well, all right. I feel pretty good about that. I hope you guys enjoyed this, and see you all next time. Cheers.